in this part, we are going to be looking at another important terms for pump design, which is called cavitation. Okay. So before we look at what is cavitation, first of all, you need to understand what is vapor pressure. Okay. So vapor pressure is the pressure required to boil a liquid at a given temperature. So for example, water will not boil at room temperature because the vapor pressure is lower than the surrounding pressure. So we can say that in our condition right now, let's say our room temperature is around 28 to 30 degrees Celsius. So at that temperature, if you look at your steam table, you can find the vapor pressure of water. So it's going to be a value. But at that temperature also, at 30 degrees Celsius, you'll have the surrounding pressure. So we can say that is your pressure of the fluid, pressure of the water. And so at 30 degrees Celsius, the vapor pressure is below your fluid pressure. So that is why your water will remain as liquid. It will not condense, it will not evaporate into vapor. So that is how water vapor works, how the vapor pressure works. So for example, now, but if you raise the water temperature to 100 degrees Celsius, the vapor are released because at 100 degrees Celsius, the vapor pressure is greater than the fluid pressure. So here you can see that the vapor pressure is higher. So that is why your water will only evaporate if the vapor pressure is higher than the pressure of the surrounding. So this, in the same manner, that is how we define cavitation in pump. So for example, now if pump cavitations occurs as the pressure in the pump, okay, the inlet drops below the, sorry, can you, your mic, someone mic is on, whose mic is on? So moving on, so let's say now cavitation will occur when the vapor pressure of the liquid is higher than the pressure of the liquid. So vapor bubble form at the pump inlet and move into the discharge of the pump where they collapse, often taking some pieces of pump with them. So this is something that we don't want to happen because it will decrease the efficiency of the pump. So cavitation is often characterized by loud noise, often described as grinding or marbles in the pump, loss of capacity. Why? Because bubbles are not now taking up the space. Pitting damage the parts as material is removed by the collapsing bubbles. Unstable, and the power consumption may be erratic, and vibration and mechanical damage such as bearing failure can also occur. So this is an image of an impeller or blade, and you can see this part here is being damaged and being chipped away by cavitation that is happening in the pump. So this is where cavitation will happen. Okay, if you have pressure, vapor pressure higher than the pressure of the fluid in this area, then you'll form cavitation. So this is an undesired condition in our pump. So again, pump can only carry liquids, not vapor. So in order for us to avoid cavitation, the pressure at the pump inlet must exceed the vapor pressure by a certain value. Now this value is called net positive suction rate, or in short form NPSH. And again, NPSH is expressed in terms of height. So the unit again here is meter or feet or inch or cm. And note, this is important, any discussion on NPSH or cavitation is only concerning about the suction side of the pump. So when we talk about cavitation, we are only focusing on the suction part. We don't discuss about the discharge part. So everything that is happening, the cavitation that is happening on the suction side of the pump. So for a small centrifugal pump, usually the NPSH is around 2 to 3 meter. For very large pump, it can increase up to 15 meter. Now the NPSH value increases with the increase of pump capacity, impeller speed and discharge pressure. To calculate the NPSH value, this is the equation that we're going to be using. So NPSH is equal to 1 over G PA minus PV over rho minus HFS plus ZE. So if you look at this equation, we are only focusing on the suction side of the pump because we are only PA is the pressure at the suction side. PV here is the vapor pressure of the liquid at that particular temperature. Rho is the density of the liquid. HFS is the friction head at the suction side, and ZA is the vertical height from the highest point in the reservoir to the center line of the pump. So this is just focusing on the suction side of the pump. So NPSH here can be defined into two types of NPSH. NPSH available or known as NPSH-A. So it is the excess pressure of the liquid over its vapor pressure at the pump section to avoid cavitation and maintain a liquid. So NPSH-A must be calculated. And then you have NPSH-R. Minimum pressure required at the suction port of the pump to keep the pump from cavitating. So NPSH-R curves are provided by the pump manufacturer. So this value we need to calculate, and this value will be given when you buy a pump. So we want to compare this value and this value. Why we want to compare? Because if NPSH-A is higher than NPSH-R, then only the pump will operate without any cavitation. So that is why it is important for us to know about this value. So if, for example, the NPSH-A is lower than the NPSH-R, the pump cannot be operated, because if we continue operating the pump will have cavitation, and which is undesirable. So let's look at an example. Example 2. Based on the information in example 1, calculate A, the available NPSH. So we want to calculate the value of NPSH-A if the vapor pressure of benzene at 37.8 degrees Celsius is 26.2 kilonewton per meter squared, and B, if the pump manufacturers specify that the required NPSH-R of 3.05 meter, will the pump be suitable for this service? So we are using all the information in example 1. So you can see here we are only focusing on this side of the pump, which is the suction side, and this is the equation for to calculate our NPSH-A. Now, so from our example 1, we know that our PA prime, the reservoir was as atmospheric pressure, so we know that the value is going to be 101.3, and the PV was given to us 26.2. Density was also given to us in the example 1, which is 865 kg per meter cube, HF is given as 3.45, and we are dividing this in, because HF was given us in terms of pressure, so we divide it by density so that all the units are same in here. So 3.45 divided by 865, and then we minus 1.22 is the height from the highest level of the reservoir to the center line of the pipe, which was given in example 1. So if you substitute all the values in this equation, you get the value of 7.22 meters. This value is our NPSHA. So the question asks us to calculate the NPSHA value and then to see whether the pump is suitable or not. So the supplier gave us the NPSHR was 3.05. So if we have 3.05 and above, then we can use the pump. Since our calculated value is 7.22, so NPSHA is higher than NPSHR. So the pump can be used for this service. So by having the value NPSHA larger than NPSHR, when we use this pump, there will be no cavitation occurring.